Hello, I am Hector and welcome to the AlphaCamp training video series from the SEM group. The topic we're going to be covering in this training session is tool definition. As you can see, we have several different types of tools that we're going to be covering the definition of through this tutorial. Um, One of the most important things to be able to successfully define tools is to have a drawing of the HSK holder. If you do not have it, and you do not want to waste time drawing, feel free to shoot me an email with the subject HSK, and I will gladly reply to that with an AlphaCam drawing of the HSK holder. What I'm really trying to say is that you will notice the tools are divided into two different categories. They're divided into the physical tool itself and just the holder. It's important to make this distinction because AlphaCam assumes that the geometry of the tool is cutting edge and the geometry of the holder is potential material that will foul your piece. Anyway, moving on. To define a tool, we need to go to Machine, Define Tool, and then choose the type of tool we're going to be defining. In this particular case, I am going to define a drill bit for a Zilog type controller for any SEM machine. This includes Morbidellis, Routex, etc. So defining a drill bit is very simple. All I have to do is click on the picture and fill out some of the parameters. For example, we'll say this tool is 2 inches long. I'm going to define a 5mm tool, and so I'm going to say 5 divided over 25.4. And the cone angle, this is interesting. Notice what happens when I put 90 or when I put 60. So if I put 180, that'll make it a flat tool. I'm going to go ahead and say fixed spindle speed of 4,000 RPM and 100 inches a minute. And that's essentially it. You see, one of the clear advantages that you have with SEM machining centers is that you don't have to define multiple drill bits for the gang bore or for the line boring. Let's say that you have 22 different 5mm drill bits. You only need to define one bit for every different diameter that you have. So I'm going to go ahead and click OK, and I'm going to save this, and I'm going to create a new folder which we're going to call tool definition. And inside of that folder, I just need to save this with a recognizable name. So I'm going to say 5mm Brad. Okay? Okay, so that tool is now available for me to use in subsequent machinings. Okay, so now the next example that we're going to be using is the flat end tool. Once again, with the same case as the drill bit, I do not need to draw the geometry of the tool. There is a template already filled out for me. All I have to do is click on that and fill out the parameters. For example, I'm filling out my tool number 101, which is going to be a 1/2 inch tool, for example. Okay? Now, on this particular one, you have values such as depth of cut and maximum depth. This is not the only depth at which you're going to be working the tool, but it is a reminder of what is the standard depth you want to work it. Also, the maximum depth is an important value because, as you can see from the shading, it'll show you which portion is actual cutting edge and which portion is the shaft of the tool. So if I ever take this tool deeper than 1 1/8 inches, I'm going to get an error message. Alright, now the next thing that I'm going to do is define the RPMs that I want to use. I'm going to say 15,000 RPM and a speed of, say, 800 inches a minute. And a down feed, this is going to be considered the plunge feed or the lead in and lead out speed. I'm going to say 400. Now, in contrast to the drill bit, any tool that you mount on a holder, it is advantageous to add the tool holder graphics. This is why I asked you previously to have the tool holder, the HSK on the screen. So I'm going to check this box. I'm going to click OK. And then I'm going to go ahead. If you read at the bottom of the screen, it's asking me to pick the holder cross section, which is going to be this one. Okay, so now I am actually ready to save this tool. Now I'm going to call this E1 because my tool number was 101. And I am very thorough with the names of the tools that I use. So this would be a 1/2 inch compression. And I actually like to add how many cutting edges or cutting blades the tool actually has. I'm going to say Z equals 2. Alright, so let's say that the next tool that I want to define is a ball end, perhaps for making flutes. So I'm going to go ahead and click on that button right here. And this is going to be tool number 102. And let's say this is a 2-inch tool with a 1/2 inch diameter and a cutting edge of 1.5 inches. You can see how the picture changes. Notice how this is pretty cool. The template does the drawing of the tool for me. There's nothing really that I have to do. Now I'm gonna reduce the feed rate because if I'm going to be fluting perhaps maple, 800 inches is a tad too fast. If you're wondering what the proper feed rate should be for a given material, the best source of information is always your tool manufacturer. They are responsible for telling you what is the allowable feed rates for a given material with their given tool. At least professional and reputable manufacturers do. Anyway, we're going to move on, make sure we have the tool holder graphic selected, and I'm going to click OK. Because I have the tool holder graphic selected, I should go ahead and select the HSK, which is this one. And we're going to define this tool as E2 1/2 inch ball end with a couple of blades. Now the next kind of tool that we're going to define is a special tool. I'm going to close this for a second to discuss this. This is an engraving tool. We're actually going to discuss each one of these machining methods in subsequent videos. But the engraving tool is a tool that I actually drew, and I placed the geometry on the screen. All of these other bits that you see right here, I did not have to draw. In contrast, a user-defined bit, which are these two, do need to have a full drawing present on the screen before you attack them. So, when I try to define the tool and I use a user-defined method, the first thing that the software is going to ask me, if you read at the bottom, is pick the geometry that defines the cross-section. Well, this is going to be this one right here. And if I'm following the sequence of numbers, this is going to be my 103. I'll probably spin this at 13,000 RPM and 300 inches a minute. As a rule of thumb, I always cut down in half the cut rate for the lead in and lead out rate. Okay, then I'm going to go ahead and click on Tool Holder Graphics, and I'm going to select that. And this is going to be my tool number E3, 90-degree engraver. And I'm going to say this has a single flute, because that's the one I physically have. It has a single flute. Alright, finally, the last type of tool, which is the more complicated tool to talk about, is a user-defined tool that has an inside diameter. You see, every time that you use a profiling tool such as this one, if you were to purchase this tool, say, in Home Depot, you will find that this tool usually arrives with a ball bearing. The ball bearing is what keeps the tool at a constant distance from your material in order for you to get your profile. Well, this line that you see right here is exactly what that is. It keeps a constant distance between the cutting edge of the tool and the material. Let me go ahead and exemplify this. I'm going to copy this out, and I'm going to put it on the right. And this rectangle that I'm drawing represents the material that I actually want to cut. You see, if we didn't have that line, the tool would always act right there, right on the edge of the material. If I put the line in the center, like we see over here, then that is going to tell AlphaCam that you want to work the tool all the way in there. Okay? So basically, the distance between this point